Okay, so we are live now. And I was trying to go onto Schoology and post something like, hey, we're here, but I'm having some difficulty getting there. Oh, maybe it's coming on now. So this will just take me a second, and then there's some questions already posted, and I'm looking forward to answering those. So I'll try to answer your guys' questions first, and then answer the questions that I've listed that I think are important. I think that if we don't get to my questions, that's fine. Hopefully your questions might cover my questions. So please post questions. Review, hang on. Okay. That, and we're off and running. Okay. There we are. All right. Excellent. We have questions. Okay. So let's start with the first question that I saw this evening, which was Jason's. He said multiple choice number 7. Now, Jason, it would help if you had posted multiple choice 7 from what? We've got 2 practice tests and the actual test. I'm going to assume you mean the actual test. That usually is what students are referring to. So let's take a look at the actual test and scroll to number 7. Which expression best describes the relationship between solubility product, which is KSP, and the solubility S of MgF2? So I'm going to go ahead and actually go to my Bamboo tablet, and I think it'll be easier for me to write this out. Once you see me write it out, I think it should make more sense. There it is. Okay. So again, we're looking for the, this is multiple choice, number 7 on the test. And the question is, you're related to, I'm sorry, MgF2. And you're wondering about KSP and S. And that's good. This is actually relates to one of the questions I'm going to talk about. This is the solubility product, or maybe solubility product constant. It can also be listed as the equilibrium constant. So that's what K is right here. And S is sometimes listed as solubility. Sometimes it's listed as molar solubility. Okay. And so that's what S is right here. And we're talking about MgF2. And you should always write the dissociation equation. So MgF2 we know is a solid because that's basically what they're telling us. And that's an equilibrium with, once it dissociates, Mg2 plus, which is aqueous, plus, oh, I didn't do that. Okay, 2, because it's got to be balanced, F minuses, which are aqueous. Okay, and the molar solubility, the S, always goes with the ion that's just a single ion. There's not more than one of it. So this would be your S. Okay, and sort of if you're doing an ice table, you know, like this, ice, okay, the solid is not a part of it at all, okay? And actually, if we're gonna do the ice table, then we might as well say these start with 0 because you don't have anything of the aqueous ions, it's all solid. And the change means you add plus S there, and because the coefficient's 2, you would add 2S here and the F minus. And at equilibrium, it's just the same thing, S and 2S. And so your KSP, which is equal to the SP, solubility product, remember it's always products over reactants. And in this case, there's nothing of the reactants. It's a 1, okay? The concentration of solids and liquids, pure liquids, are always 1. So that means it's just the products, okay? So we then would have KSP is equal to the concentration of Mg2 plus times the concentration of F minus, okay, and F minus squared. And we already said what that is going to be. So KSP is equal to S times 2S squared, which is equal to 4S cubed. Okay, so we need to go back to that worksheet and we're going to be looking for 4S cubed. So let me share that document again. And where is it? Okay, there it is, right? Is that? Oh no, did I share the wrong one? Doggone it. And I did the practice test. Ha. Okay, let's look at the, I'll go back and do the, oh my goodness. That was not a good use of time. Okay. All right, the answer is D. So you guys might all be thinking that's pretty easy. Hopefully, Jason, that wasn't your question. Or maybe that was, but we're gonna do the practice test, or the regular test now. I apologize. Ironically, that totally ties into 2 other questions. I think it ties into Efrain's question and one of my questions later on. So it wasn't a total waste, actually. Where is the test? Equilibrium test. Is this it? Equilibrium test. Unit test. Is that on the screen now? Number 7. Consider the reaction. Oh, this is actually easier. How fortunate. You have a reaction. It says consider this reaction with this K, which is 49. What is the value of K for the following reaction? And what they did is they took their reaction and they flipped it, and then they multiplied the whole thing by 2. Once you flip it, it's 1 over K, which is 1 over 49. And then when they multiplied everything by 2, that means you square it, make the exponent on the K. If they multiplied it by 3, it would have been 49 to the 3rd power. So your answer is C, because you flipped it and multiplied by 2. So it was 1 over 49 and 1 over 49 squared. So that's actually the answer. Hey, yay. Okay. All right. So now we'll go to Efrain's question. What is KEQ? So I'm going to go ahead and share the document, kind of the bamboo paper, and just kind of continue with that. So Efrain, KEQ is the equilibrium constant. And it's calculated by the products over the reactants. Concentration of the products over the concentration of the reactants. And it represents the point in a reaction in which the concentration of the products and reactants remains constant. A K exists when you have a reaction that goes forward and backwards. Remember that K is, the definition is the rate of the forward reaction equals the rate of the reverse reaction. And so when you have that equilibrium, so for example, N2 plus 3H2 is in equilibrium and making 2 NH3. So it's going to the right and it's going to the left. And when those rates are the same and the concentrations of each remain constant, they don't have to be the same. The concentrations are not the same. But when the concentrations remain constant, the concentrations don't change because the rates are the same, then you have equilibrium. And that's calculated with product of reactants. And that's kind of what I was getting to over here. We talked about this, right? We're calculating that in a situation where you have the solubility process, where you have something that's insoluble and it's a solid dissolving into its aqueous components. The solids are always one, so it's just products. It's not products over reactants because the reactants are solid. Okay, so that takes care of Efrain's question. All right, next question I saw was Aria. So for response number 1A on the test. So let's share the test again, at least what I hope will be the test. Okay. Okay, good. So for response 1A, write the expression for the solubility product constant KSP and calculate its value at 18 degrees Celsius. So we've been talking about the KSP, and remember that it's products over reactants. And in this situation, MgF2, very similar to what we were doing already in the bamboo tablet. There is no solid. And so that the solubility, the expression for this, like this up here, this is the dissociation equation, okay? This is the expression for the K, for the expression for equilibrium constant, or expression for solubility product constant. And that's just writing that K is equal to the concentration of Mg2 plus times the concentration of F minus squared. And you remember that it's squared because, of course, it takes 2 fluoride ions for every 1 Mg2 plus ion. Now, if I put this in here, it's S times 2S squared. Okay, so I can make that like that. Okay, and the S is the 1.21 times 10 to the negative third. Okay, if you remember, I said that the whichever ion is just single, there's not multiples of it, that is the S for this, for our case. So there's S, 1.21 times 10 to the negative third. Then 2S, you have to double 1.21 times 10 to the negative third, and then square it on the outside. And then you multiply that together. Now, in this situation, in this question, they just give you the molar solubility. They say it's saturated. And so S is molar solubility, or solubility. It's when it's totally saturated, which is what you have here. Mm-hmm. So you have you are given these and said, okay, this is what it is, or when it saturates this. So what could the K be? Which is different than the later question. Where is it? Well, there's a later question down here. Like, they're giving you some concentrations to work with. They're giving you some concentrations of each one to work with. But in the first one, they just give you the concentration of one and say it's saturated, so what's K? So you know what Mg2 plus is, so what does F2 minus or F minus have to be if Mg2 plus, if it's a saturated solution? If they give you both concentrations, then you're going to be kind of be plugging it in, and you're going to have to multiply the concentrations together. But that's why you double this, because they gave you the solubility. So that's 1A. Okay. The next one I saw was Mary Flake. So she wanted free response number 1B and D on the actual test. And we are already there. That works out really well. So 1B, the question is, change real quick. I think my key is a small mistake, not that it's a big deal. So it wants to know that in the test, they're asking for the concentration, the equilibrium concentration of Mg2 plus. So once it's reached equilibrium, what's that concentration of Mg2 plus? And so you can see a whole lot of work right here. And you know what? I'm gonna do this on the bamboo paper because I think that it'll be an opportunity for me to explain it a little bit clearer. Okay. So Share that. Excellent. Okay, let's go to the next page on here. Oh, next page again. All right, so now we're on number 1B and D, or I should, since I use lowercase, totally not an important thing to worry about for your response test. Okay, number 1B. Now we've already established that the KSP is equal to 7.09 times 10 to the negative 9th, okay? And the only thing that changes K is temperature. The only thing that changes K. So K is going to remain the same. And if you remember, KSP is going to be equal to the concentration of Mg2 plus times the concentration of F minus squared, okay? So if K stays the same, it's constant. If the amount of F minus increases, then the amount of Mg2 plus has to decrease. I always use the example of, okay, so 4 equals 2 times 2. But now I'm going to take this 2 and I'm actually going to change it to 4. And my first 4 stays the same. So what does this have to be equal to? What times 4 is equal to 4? Well, this has to be 1. So that meant that the 2 went down, whereas the 2 over here went up when it went to 4, okay? Because they still equal 4. So you're going to have to decrease the concentration of Mg2 plus. Its equilibrium concentration is going to be less than what it was before. Before, it was 1.21 times 10 to the negative third, okay? Now, we just, in 1B, we just overloaded it with Kf. There was 0.100 moles of Kf, which dissociates completely into K plus F minus. So you are getting 0.100 moles of F minus. It's in there, okay? So in this situation, you're saying, oh, wait, the MGF2 was already in there before this, but for the sake of this, to make it quite a bit more simple, you really need to set up an ice table as if the Kf was in there first, okay? So if we have MgF2 solid in equilibrium going to Mg2 plus aqueous plus F, it's 2F, got to balance it, F minus aqueous, okay? And we have our ice table, okay? This goes away entirely. There's 0 of the magnesium 2 plus, and I said we have to assume, it would be easier just to assume that the 0.100 moles was already there of the Kf dissociated. There's a ton there. So what's going to happen is, if you now add the MgF2 in there, according to this, because the way I'm going to do it, and I think I might have explained it a different way last time, I'm going to use a different way this time because maybe explaining it differently will help you guys. If I'm adding the MgF2 in there now, as if the Kf was in there first, okay, the MgF2 is going to dissociate a little bit, but not nearly as much as it did before. So you're going to dissociate just a little bit here, okay? And you're going to dissociate just a little bit more into that same solution, okay, for the F minus. Okay, not a ton, but you're going to dissociate a little bit. So what does that mean? What is that going to look like? Well, at equilibrium, you're going to have just that little bit, and now you've got 0.100 plus 2x, because you dissociate just a little bit. Now remember, for this, if K is less than 1 times 10 to the negative fourth, then this becomes negligible, okay? So really, that means that's really just 0.100, okay? The 2x just goes away entirely. So now I'm going to run this calculation. Remember, my K stays the same. KSP is equal to Mg2 plus times F minus squared. Now, this is not a 2x situation. It's not we're not doubling this. This is telling you this is the concentration, okay? So that means KSP is equal to x times 0.100 squared. And if you remember, KSP is equal to 7.09 times 10 to the negative 9th equals x times, and if you did 0.1 squared, you get 0.01. And then you need to divide both sides by 0.01. And basically that's like multiplying times 100. Anyways, you plug it into your calculator and you get 7.09 times 10 to the negative 7th is equal to x. And if you remember, x is equal to the concentration of Mg2 plus. So now that's equal to 7.09 times 10 to the negative 7th. And this is quite a bit smaller than the original concentration of 1.21 times 10 to the negative 3rd. That concentration of Mg2 plus dropped precipitously. I mean, it really went down. Okay. So that is 1B. So now let's scoot on down to 1D. And so let me go back and share the test so you guys can see it. Okay, 1D. So now at 27 degrees Celsius, the concentration of Mg2 plus in a saturated solution is 1.17 times 10 to the negative 3rd. Is the dissolving endothermic or exothermic? And give an explanation to support. Okay, so what they did is the original temperature, if you look up here, was 18 degrees. So at 18 degrees, the concentration of the Mg2 plus was 1.21 times 10 to the negative 3rd. And then you increase the temperature to 27 degrees and the concentration of the Mg2 plus dropped to 1.17 times 10 to the negative 3rd. So let me show you the bamboo tablet. And there we go. All right. So this is free response 1D test. Okay. So if we have, I'm sorry, let me rewrite this so you guys can see it. 18 degrees, 1.21 times 10 to the negative 3rd. 27 degrees Celsius, 1.17 times 10 to the negative 3rd. And our equation is MgF2 solid in equilibrium with Mg2 plus aqueous plus 2F minus aqueous. Okay, now what's happened is they have caused a shift by increasing temperature, a shift going this direction. Okay, and by just increasing temperature. Now, so you have to look at it like this. Remember, I like the teeter-totter. If we make this an endothermic reaction, that means that heat is on this side. And if we increase temperature, okay, that would be the same as pushing this side down, which now it's like this. Okay, so if it's endothermic, we push heat down, that means that it's gonna, the equation is gonna shift to the right to get back to equilibrium. It's gonna favor the products, which means that the concentration of Mg2 plus should go up. But that is definitely not what happened, okay? What happened was, make another teeter-totter here, okay? Heat was on the right, okay? Heat was a product. So when we increased the temperature, we added it to the right side. So now the teeter-totter is this side, so now it's gonna shift to the left. It's gonna favor the reactants, which means it's gonna use up, it's going to consume magnesium 2 plus. The concentration goes down because it's consuming magnesium 2 plus to produce more or create more MgF2, right? So that's why it's exothermic. Increasing heat will, on this situation, the reaction will shift to the left to reestablish equilibrium, and you will consume product. In this case, it's consuming magnesium 2 plus, and it will create more MgF2. Now, another question that could be asked that's not here is, well, what does that do to the K? So I'm gonna make that orange because that's good. Okay, equilibrium. What happens with that? Okay, well, if you create more reactant and consume product, remember that it's equal to product over reactant. And if the amount of product goes down and the amount of reactant goes up, and in this case, it doesn't matter because it's a solid, so it's not really a product, but the amount of your product goes down, K equilibrium, or KSP, goes down in a situation like that. So you need to be aware of that. On the test, there'll be questions like that that will ask you. So that answers Mary's question for 1B and 1D. Good. All right. The next question that I had seen was Mikey, and he would like 2B, C, and D. Okay. So let's go back to the test. And two B, C, and D. Okay, 2B. This is the KP and KC. Now, there will not be a question like this on the AP Chem exam itself, I don't believe. The only thing that I think that they will ask about is the relation of KP and KC in relation to the change in moles of the gas, okay? And so I'm going to switch to just for a second, switch back to the Bamboo tablet. Okay. Sorry, give me one moment. Okay. So, oops, I don't want that. I would like blue. Okay. So this is 2B free response test. Okay. KP versus KC. All right. And so really the equation this relates to is that KP is equal to KC times RT to the delta N. Okay. So KC is concentration. KP is the equilibrium of pressure, usually of gases. So concentration can be gases too, but anyways, they're related to each other. R is the gas constant, T is temperature, and delta N, N is the moles of gas. Oh my goodness. Delta N is the change in moles of gas. Change in moles of gas, okay? So if you have an equation like the one that was on the test, and you had CO2 as a gas plus H2 as a gas is in equilibrium with H2O as a gas plus CO as a gas, okay? So KP equals KC times RT to the delta N. Oh, and delta N is products minus reactants. Okay, this is very similar to Hess's law. Like a lot of things are products minus reactants in chemistry. So delta N, which is equal to 2 moles of products minus 2 moles of gas. There's 1 here, 1 here, 1 here, 1 here. So 2 minus 2 equals 0. So really what that comes down to is KP is equal to KC times RT to the 0, okay? This makes this go to 1, which means that KP equals KC. So when your moles of gas are equal on both sides of the equation, KP is equal to KC. That's all that's asking you for. That's the one thing I want you to be able to pull out of that. Okay, so let's go back and go on to C. Okay, C. Now this question is, well, what happens when 30% of the CO is converted back to CO2? Oh, excuse me. So it doesn't tell you what the new temperature is, and it doesn't matter when you calculate K. Like, you're never using temperature in the calculation of K. Not never. I just finished one where you had that, but you're not usually using it. So what we do though, and I think this one does a pretty good job of showing this, so I'm not going to go to the bamboo paper on this. Basically, you have these values for the H2, the CO2, the H2, and CO. All right, so you put those are all the initial values for their concentration. It says 30% of the CO is a product, is converted back to CO2. So you have to take the 0.55 times 0.3, that's 30%, and you're losing that amount. So subtracting minus 0.3 times 0.55. Now, we just got finished saying that all of the coefficients are 1. So that means it's the same change for every substance. The CO and the H2O are both losing that amount, and then the CO2 and the H2 are gaining that amount. So once you plug all that in, it gives you new equilibrium values for each of the substances, okay? Once you have those equilibrium values, then you just plug it into your K. Remember, products over reactants. And it turns out that the products are the same, so 0.385 squared divided by 0.365 and divided by 0.465, and your new K becomes 0.87. So I think that probably makes sense. I mean, it was probably hard to wrap your head around what's the 30% thing, but when it asks you that, that's the change. Whatever that quantity is, it's, oh, this percent, 65% goes, or if it were to say 65% remains, then you know that you're going to do 35% times whatever the concentration is. You just remember that you have to multiply it times the original concentration. All right, and then D, different experiment, 0.5 moles of H2 is mixed with 0.5 moles of CO2 in a 3-liter reaction vessel at 2000 K. Okay, calculate the equilibrium concentration in moles per liter of CO at this temperature. All right, so you can do it in just straight moles, or you can do it concentration. I don't like to mess around with, oh, when do I change it? I just like it to be in the units it needs to be in the whole time. And if you need, your answer needs to be concentration, let's just change it to concentration right now. I think that makes it easier. So 0.5 divided by 3 gives you a 0.167. So that's the same concentration for CO2 and H2. Now, it says that it's mixed together, and it does not mention the concentrations or the number of moles of your products. To me, that means that it's 0. That's not to me, that's what it means, it's 0. And since it's 0, we know that the reaction is going to proceed to the right as it approaches equilibrium, which means you're going to lose a certain amount, X, from each side, and you're going to gain a certain amount, X, on the other side. Remember, the coefficients are all 1, so it's just minus X and minus X on the reactant side, plus X and plus X on the product side. So you end up with a 0.167 minus X for your 2 reactants and plus X on your product side. If you remember that it is the K for this is not less than 1 times 10 to the negative 4th. It's actually a very sizable K. So with that being the case, you cannot make the X negligible in the 0.167 minus X. It must be taken into consideration, which isn't too bad because it's just X squared over the difference of 0.167 minus X also squared. And so what I would do is take the 5.04 and square root that. Actually, why don't I show you? Because inevitably somebody will be not sure how to solve that one. This is math though, and you need to be getting better at this. It needs to just not come to you, but you need to be prepared to do this kind of math. AP, College Board, will expect an AP Chem student to be able to do this kind of math quickly and effectively or efficiently. So we were left with a K is equal to X squared over 0.167 minus X squared. So that means that it's 5.04 equals still X squared, or 0.167 minus X. Oh, I'm not substituting in yet, anything yet. So then I square root both sides, okay? And this is for response, so you do have access to a calculator. I don't know this stuff right off the top of my head. Square root of 5.04 gives me, so I have 2.24 equals x over 0.167 minus x, okay? So then I'm going to multiply both sides by 0.167 minus x, and oh, sorry. Let me do this. Give it space. If I'm going to do it, I might as well do it right. Correct? So that's 2.24 is equal to x over 0.167 minus x. So I multiply this side by 0.167 minus x, and I multiply this side by 0.167 minus x. Okay? And so these cancel out. And I'm left with x is equal to a 0.3749 minus 2.24x. And I'm going to add 2.24x to both sides. I think this is right. If I mess this up, so help me. Okay, so that means this is going to go away, and you're left with 3.24x equals 0.3749, and you divide both sides by 3.24, and your x is equal to, good, 0.12 molarity, and we already said that x is equal to, what are we looking for? Of the CO, because x is CO. That's the concentration of the CO. Yay, done. Shazam. All right, 2B, C, and D. Good. All right, so now I kind of got lost a little bit on which questions came in first. Let's see if we have something that kind of flows with this. It looks like Ephraim's question got a couple pluses as well. Test free response 1C. We've already done 1A, B, and D. Might as well do C. So, kind of share the test. Oops, 1C. Okay. So I'll have to do this on bamboo paper. I can feel it. So you're predicting if a precipitate will happen if you have 100 milliliters of this concentration of MgNO3 and this volume of the concentration of NaF. Doesn't matter what the temperature is. So you've got things that dissociate. Nitrates and alkali metals dissociate completely. So you're going to have this amount of magnesium and this amount of F. And you are going to have to multiply them together. Fantastic. All right, let's get that bamboo paper going. All right. So this would be free response number 1C on test. Okay. All right, so for we want to know MgF2. That's our question. Okay. We have for the concentration of MgNO3 2, which is actually equal because it's a 1-to-1 ratio. For every 1 mole of magnesium nitrate, you get 1 mole of magnesium. So that's the concentration of Mg2 plus is the same as that concentration. So 100.0 milliliters of 3.00 times 10 to the negative third molar, okay? And we're gonna combine this with a 200 milliliter concentration of 2.00 times 10 to the negative third molar, right? So this is the Mg2 plus. Oh, and I should do that too. The NaF, the concentration of that is equal to the concentration of F minus. Because it's a 1-to-1 ratio. For every 1 mole of NaF, you get 1 mole of F minus. All right, so what I need to figure out is how many moles, how many, basically what is that concentration if we're gonna multiply that together. And so what I would say is, what's the quickest way to do this? Why don't we do this? So for the Mg2 plus, all right, that's equal to 3.00 times 10 to the negative third, and that's the number of moles in 1 liter. But what we're gonna say is that's molarity, which is moles per liter, times, that's the concentration. Why am I struggling with this? There's actually 0.3 liters, right? Oh, I know why I'm struggling with this. Because we want the concentration again. I know, because I'm going for moles. So really what this means is we have 100, because if we multiply this times 100.0 milliliters, that gives us the actual number of moles. So multiplying it times 100 milliliters, which is what we had right here, will give us the number of moles in this. However, the total volume, because we want this in concentration, is 300.0 milliliters, okay? And really, I mean, technically we should make it in liters, but the milliliters are gonna cancel out, so it doesn't matter. So basically we're taking this amount and we're multiplying it times 1/3, okay? So that means that's gonna be equal to 1/3, isn't that like just 1? Yeah, 1.00 times 10 to the negative third molarity, okay? So that is the concentration of the Mg2 plus once they're mixed together. The concentration, oh, not the N, we want the F minus. Oh, how about the eraser? There we go. Okay, so the concentration of the F minus is equal to 2.00 times 10 to the negative third molarity times, now we had 200.0 milliliters, and so multiplying it times that volume will give us the number of moles. And remember that the total volume was 300 milliliters. So you're multiplying 2 times 2/3, which comes out to 1.33 times 10 to the negative third molarity, okay? So this is our Mg2 plus concentration, and this is our F minus concentration. That is the actual concentration, okay? This is not these are not the molar solubilities. These are the actual concentrations. If we have the actual concentrations, then we can find out the K. Now, unfortunately, this is not really K, so I need to erase this. This is actually Q. We don't know if this is at equilibrium. So we're actually solving for Q first. Q. So Q, which is the same thing as K, we calculated the same way you would solve for K. But Q is when you don't know if it's at equilibrium or you know it's not at equilibrium. Okay, so we're still doing Mg2 plus times F minus squared, which has been our same thing the whole time, which means that it's Mg2 plus, which is 1.00 times 10 to the negative third molarity times 1.33 times 10 to the negative third molarity squared, okay? So Q is, once I multiply these together, 1 exponent negative 3 times 1.33 exponent negative 3. Oh, I forgot. I got it because I got to square that 1.33. So 1 times 10 to the negative third times 1.33 times 10 to the negative third squared, And that should give us the almighty, what do I get here? My calculator says 1.7, we'll say 1.77 times 10 to the negative ninth, okay? And if we go back to the original problem, and because that was C, if we go back to A, we know that K, the actual K, is equal to 7.09 times 10 to the negative ninth. Okay, so they're actually pretty close, but we put the K right up here. K is, wait, am I doing this right? Suddenly I'm doubting myself because I do that a lot. Yes. So K is larger than Q, right? K is larger than Q. And if you remember, the way that I wrote this, or I tried to write this, the trick is you write the K first, you write the Q second, and whichever way the alligator points is the direction that the equation, or the direction that's favored, okay? And so this is the one where MgF2 is the solid on the left and goes to the right, where the Mg2 plus aqueous plus F minus 2F minus aqueous. So it's favoring the product side, which means that it's going to be, it's not going to form a precipitate. So the answer is no, it's not formed, okay? So, you know, your justification can't be, oh, because the alligator points to the right. But what you can say is that in a situation like this, where the Q is less than the K, that means that the products are smaller. The concentration of the products are actually smaller than they would be at equilibrium, okay? And in order to get back to equilibrium, it's going to have to favor the product side to get back to equilibrium, okay? So actually, let me if K is greater than Q, then, or therefore, you could say, current concentration of products is less than equilibrium concentration of products. So reaction favors products to reestablish equilibrium. Therefore, no precipitate favors aqueous ions. So you need to be able to explain that as well as do the calculation, but hopefully that makes sense to you guys. Boy, that first was a doozy. It was a doozy. All right, good. All right, that's done. All right, now let's look at some other questions. So let's see. I think I saw Ephraim's question about why KQ seems to be the inverse of KC. So I have no idea what you're referring to, Ephraim. K equilibrium and KC are essentially the same thing. There is no inverse of that. So, or maybe you're speaking of a particular problem, but since I don't know what you're talking about, I'm going to have to say that that's not a true statement. So we'll just leave that one alone. But you can maybe ask another question later and could try to tie it in. So make that one done for right now. I think I saw Arya's next. How can you, so let's do this one. How can you tell if something is negligible? And so Arya, what we've said is, so X, or the change in concentration, that's That's what we're referring to, concentration. I could just abbreviate that. So that is negligible if the K is less than 1 times 10 to the negative fourth. That's how you know. If the value of K is less than 1 times 10 to the negative fourth, then X is negligible. And it's always referring to a situation like in an ice table where you have a 0.25 minus X. Well, then the X is negligible if K is equal to 5 times 10 to the negative 13th. Okay. In an earlier one, let's see if we can find an ice table I can show you real quick. Okay, here. So the change, it's usually when you're talking about common ion too, that's when you're talking about negligible. The change was 2x. When is that negligible? If the K is less than 1 times 10 to the negative fourth. And the K was 7 times 10 to the negative ninth. So that's why that one was negligible. So hopefully that helps explain that one. Okay, next up. Aria had a question on number 5, multiple choice number 5 on the test. So let's take a look at that. I'm going to share the test. Okay. All right. Consider the solubility equilibrium represented by the equation below. It's a lead sulfate dissolving into its 2 ions. The addition of K2SO4 to this system will cause. Okay. So actually, let's do the bamboo tablet and let's walk through the different possibilities that could happen. Create a new page. All right. So we have, oh, I should write what this is. So this one is multiple choice number 5 on test. We have PbSO4, which is solid, in equilibrium dissolving into Pb2 plus aqueous plus SO4 2 minus aqueous. All right. And you're adding, if we did an ice table, just an example, and you're adding K2SO4, K2SO4. And because this is an alkali metal, you know you're going to get a whole bunch of SO4 2 minus, okay? So that's a whole lot. We'll just say a lot here, okay? So now what we're looking at is kind of an equilibrium thing, right? We just added a whole bunch of product. Great. We just added a whole bunch of product, okay? This really doesn't start as, well, it doesn't have to necessarily start at 0. Let's say, well, it doesn't matter. The question is, maybe I didn't have to do an ice table for this one. Maybe it's just this one right here. You add a whole lot to that side, and now it looks like this. The reaction is going to go back to the left. It's going to favor the left-hand side. It's going to favor the reactants, okay? Which means that if it goes back this way, it's going to consume Pb2 plus and SO4 2 minus. So the concentrations of Pb2 plus and the concentration of SO4 2 minus will go down. It will go down. And the concentration, and there's really no concentration, but the amount of PbSO4 should go up. The concentration is equal to 1, but the amount might increase, okay? So looking at that thought, okay, we now need to go back to that question and see if we can figure out which of the answers would be and why. Okay. So it said the addition of, so we know that there's less SO4 and Pb and more PbSO4. So it says that the addition will cause Pb2 plus. We know it decreases, so that means that these first two out, the answer can only be C or D. And then says that the PbSO4 in the system decreases. Well, we just said the PbSO4 would actually increase, so that means the answer has to be D. Oops, totally messed that up. Good thing we have the back button. Okay, so hopefully that answers number 5. We finish with that. All right. And Ephraim, multiple choice number 4. So that is, of course, right above that. What is the molar solubility in water of silver chromate? In the case B is 8 times 10 to the negative 12. So let's do this on the bamboo paper so you can see it. All right. This is, oops, I want to do this in blue. Multiple choice number 4 on test. Okay. Molar solubility. And just for clarification, molar solubility is S. That's molar solubility. And molar solubility always refers to the ion that there's just one of. And we have Ag2CrO4 as a solid in equilibrium dissolving into two Ag pluses in aqueous plus CrO4 2 minus as an aqueous. Okay. And if we did an ice table, the solid would not be there. And molar solubility S, it's the ion that is only one of. So there's S. This is 2S, right? I jumped the gun just a wee bit. These are both initially 0. Then it's S for that and 2S here, okay? And at equilibrium, it's plus 2S and plus S. So K, which is the solubility product, is equal to the concentration of Ag plus squared, because there's 2 of them, times CrO4 2 minus. And the KSP, we are told, is 8 times 10 to the negative 12th. So that's equal to 2S squared times S. So that's 8 times 10 to the negative 12th equals 4S squared times S. So I'm going to switch sides really quick and make it 4S cubed is equal to 8 times 10 to the negative 12th. Divide both sides by 4. So now we have S cubed is equal to 2 times 10 to the negative 12th. And it's a multiple choice, so we don't have a calculator for this. So we're going to do a cube root of both sides. So that's the same thing as saying S is equal to 2 times 10 to the negative 12th to the 1/3 power. And so we go back to the test and see if that is one of our choices. And hopefully I did that correctly. Number 4. D, 2 times 10 to the negative 12th to the 1/3. Yes! Score! Get that one right. Okay. This is good. This is really good. Being able to do these, it's like writing an expression is also what will be on the test. So that's good. I think if you guys really learn from this tonight and you've done both practice tests and you review the actual test, I think that you'll do well on this retake. I really do. Not just as a teacher. I feel it deep down. All right. Other questions. Let's see what we've got here. Ephraim, why did Ag turn into 2S squared instead of just S squared? Well, Ephraim, let's go look at the thing again. We've been saying this all night, that if you're given the concentration, you just plug the concentration in. But when you're finding the molar solubility, the coefficient is 2. Look, the coefficient here is 2. So that's why it's 2S. Okay? The S goes with the CrO4 because its coefficient is 1. If I go back here, if we did these, the change would just be S and S because the coefficients are 1 and 1. Let's go back to another one. Here we go. Okay, the coefficient is a 1, so it's a 1x. The coefficient is 2, so it's a 2x. Let's see if we have another ice table. Do I have any more ice tables? Did I do it? Oh, here I did. Okay, there's a 1 in front of the mg, so it's a 1s. There's a 2 here, so it's 2s. Okay, so hopefully that makes sense now. When you're doing the expression, the solubility constant or solubility product expression, and you're dealing with molar solubility, whichever one has a coefficient of 2, that becomes 2s. All right. So that answers that question. Looking at my questions. Review of Le Chatelier in effect on moles, concentration of species in K. Okay, so we covered this one earlier, this question that I asked. You need to know the teeter-totter, the review, of Le Chatelier's principle. And let me go back to the one where that actually is probably the most, there's a couple of them. So here, the teeter-totter, if you consume the products and it will shift back to the reactant and produce reactant. Well, that will do decay. If you lower the concentration of the products, you're going to lower the value of K. So that's how that works. Is there another problem like that I think I talked about? Here we go. Yeah. So you increase the temperature, and that was exothermic because it decreased the concentration of Mg2 plus. It shifted to the left, consuming the Mg2 plus and the 2F minus, lowered the K because there were less products. Good. All right. So you guys have seen that. You can go back and listen to some of that. All right. Next question. How does common ion affect equilibrium? We did that one already as well. Common ion effect, I did an ice table. Where did I do that ice table? I must have done it early on. Yes, the MgF2. Okay, so in this one, when you have a common ion, that it's easier just to say that it was there first, and then say that a little bit of the MgF2 dissociates. And really it's more about the Mg dissociating at that point because you have so much of the F minus, you have so much of that ion, whatever that common ion is, that whatever dissociates is negligible, right? That's what this change is. So whatever dissociates is negligible, it goes away. You're staying with the amount that you originally have. And then you do that calculation. So the concentration of the magnesium must go down in order for that to work, because it was 1.21 and now it's up to 7.0. I'm sorry, it was 1.21 and it went down to, it was originally 1.21 times 10 to the negative third. With the common ion, it made that concentration move down to 7.09 times 10 to the negative seventh. So there is a common ion effect question on there, so you need to make sure you're familiar with that. And finally, and we've been talking about it a ton, molar solubility and solubility refer to the S's. That's all that is. So I think I talked about that in the very first page. Yes, molar solubility and solubility refer to the S's. Okay. So when you see those words, that's what that means. And equilibrium constant or solubility product constant or solubility product, that refers to the KSP. So it refers to the expression. You're doing K is equal to products over reactants. If you're having a balanced reaction, you are dissociating the solid into its aqueous ions. Okay. So I think we covered all the things that I felt like were important, and hopefully we covered all the things that you really wanted to know about that you were unsure of. I'm going to make every effort to be there by 6:15. And if you want to show up a few minutes early and ask me questions, you're more than welcome to do that. And then start the retake at 6:30. And I know that some people had already spoken to me about needing to come in at lunch. And I think somebody might be coming in after school, which should be fine. But I do feel like you guys will do well on this test. So since I don't see any other questions, I was going to end it here. Are there any other questions? I'll give you like 10, 15 seconds to write something down. While you're doing that, just going to wait. Give myself a silly hat. It's a party. No. I have a puppy too. But I'm an angel. Okay. All right. Enough of that. All right. Any other questions? I don't see any. All right, you guys. Have a great night and get some rest. Make sure you get some sleep. That's the most important thing. And we'll see you guys tomorrow morning or tomorrow sometime. All right.